Two observations have shaped the foundation of the information technologies that permeate every aspect of our business and personal lives. First, observing how humans perform operations on numbers led to using general-purpose digital computers. Second, observing how neurons in the brain might be mimicked using digital computing algorithms led to robotics, intelligent decision-making, and generative AI. However, new observations from neuroscience, genomics, and the general theory of information point to new directions for information technologies. Late Professor Mark Burgin's observation that knowledge belongs to the realm of mental structures and in biological systems knowledge to information is as matter is to energy provides the groundbreaking work on the general theory of information, GTI, which bridges the gap between the material world, matter and energy, and the mental world of biological systems, information and knowledge. Autopoiesis refers to the behavior of a system that replicates itself while maintaining identity and stability despite external fluctuations. Cognitive behaviors involve modeling a system state, sensing internal and external changes, analyzing, predicting, and taking action to fulfill its functions. Burgin's work contributes to understanding how information, cognition, and autopoiesis intersect, shaping both biological and digital systems. This video discusses the use of GTI, integrating current computing structures and the impact on next-generation computer science and information technologies. This picture shows the relationship between data, information, data structures, and algorithms in the design of symbolic and sub-symbolic computing structures. Symbolic computing consists of programs or algorithms represented as sequences of symbols operating on data structures represented also as sequences of symbols. Sub-symbolic computing receives input from various sources converted to sequences of symbols and is processed through an algorithm that represents a neural network with optimized parameters that produces output. Transformers are neural network architectures that track relationships between chunks of data and derive meaning from them. They were introduced by Google in 2017 and are based on the multi-head attention mechanism. This attention mechanism allows the model to focus on different parts of the input data with varying degrees of emphasis. Generative AI, Gen AI, analyzes vast amounts of data, looking for patterns and relationships, then uses these insights to create fresh, new content that mimics the original data set. It leverages machine learning models, especially unsupervised and semi-supervised algorithms. Transformers allow AI models to understand the context and relationships in the data, much like how we decipher the words in a sentence. This understanding is then used to generate diverse content, from graphics and multimedia to text and even music. There are three popular techniques for implementing generative AI: generative adversarial networks, GANs, variational autoencoders, VAEs, and transformers. Transformers have been widely adopted for training large language models, LLM, on large data sets, such as the Wikipedia corpus and Common Crawl. This architecture is now used not only in natural language processing and computer vision, but also in audio, multimodal processing, and robotics. One of the examples of transformers in generative AI is the generative pre-trained transformers, GPT, a type of large language model, LLM, that uses transformers for natural language processing tasks. Super symbolic computing structures suggested by the late Professor Mark Burgin use the structural machine and knowledge structures derived from the general theory of information, GTI, to provide an overlay over symbolic and sub-symbolic computing structures with a common knowledge representation. GTI provides a bridge between our understanding of the material world consisting of matter and energy and the mental worlds of biological systems which utilize information and knowledge to interact with the material world. His construction of a new class of digital automata to overcome the barrier posed by the Church, Turing thesis, and his contribution to super-symbolic computing with knowledge structures, cognizing oracles, and structural machines provide a new approach to the future design of information technologies with super-symbolic computing. The new MIT Computer Science and Artificial Intelligence Laboratory, XAIL, frameworks provide important context for language models that perform coding, AI planning, and robotic tasks 1. These frameworks are LILO, library induction from language observations, which can synthesize, compress, and document code. ADA, action domain acquisition, which explores sequential decision-making for artificial intelligence agents. LGA, language-guided abstraction, helps robots better understand their environments to develop more feasible plans. These frameworks use natural language to boost the performance of large language models, LLMs, in these tasks. The next two pictures show a schema designed using functional and non-functional requirements and best practice policies and constraints, and its implementation using Python, containers, a graph database using a cloud infrastructure as a service, IaaS, and platform as a service, PaaS. Another video describes the schema details and its implementation. The concepts are explained using a video on demand service with autopoietic and cognitive behaviors.